Hello, greetings to you. My name is Ramesh, 21951 A04 F0 of branch ECE section C. In this presentation, I am going to talk about thermal conductivity in semiconductor thin films and nanowires. What is thermal conductivity? Thermal conductivity, often denoted by K, lambda, or K, refers to the intrinsic ability of a material to transfer or conduct a heat. It is one of the three methods of heat transfer, the other two being convection and radiation. Heat transfer process can be quantified in terms of appropriate rate equations. The rate equation in this heat transfer mode is based on Fourier's law of heat conduction. It is also defined as the amount of heat per unit area, heat per unit time per unit area that can be conducted through a plate of unit thickness of a given material. The faces of the plate differing by 1 unit of temperature. Thermal conductivity is quantified using the international systems of unit SI unit of W by M into K, watts watts meter watts per meter per degree Kelvin, and is the reciprocal of thermal resistivity, which measures an object's ability to resist heat transfer. Thermal conductivity equation can be calculated using the following: K is equals to Q into L by A into T2 minus T1, where Q is equals to heat flow W, L is equals to length or thickness of the material M, small m, A is equals to surface area of the material meter square, T2 minus T1 temperature gradient K. In this talk we present a self-consistent model for calculating the lattice thermal conductivity in semiconductor thin films and nanowires. The model is based on the solution of the Fonon-Boltzmann equation. It is rigorously takes into account modification of the acoustic phonon dispersion in low dimensional structures with the lateral feature size of 10 nanometers to 30 nanometers and change in the non-equilibrium phonon distribution due to partially diffuse scattering from rough boundaries and interfaces. The Fonon-Boltzmann equation properties and link to weakly and harmonic lattice dynamics. For low density gases, the validity of the Boltzmann transport equation is well established. The central object is the one particle distribution function f in f, which in the Boltzmann grade limit satisfies the Boltzmann equation. It is shown that the presence of distinctive boundaries in such structures leads to a transformation of the acoustic branches of phonon dispersion to quasi-optical branches characterized by a low group velocity and different cutoff frequencies. This transformation affects both in plane and cross plane thermal conduction in low dimensional structures. In this, we also analyze three phonon amclap scattering process in thin films and nanowires and compare them with those in bulk semiconductors. The predictions of the thermal conductivity. The described changes in phonon transport in semiconductor, thin films, and nanowires bear important consequences for nanostructure and device simulation, since neither Fourier beat theory nor D approximation are accurate at nanometer length scale. The observed modification of the thermal resistance of the low dimensional structures has to be taken into account in simulation of thermal transport in deep submicron devices, since it strongly affects the electrostatic discharge voltage EDS and other reliability characteristics. The change in the acoustic phonon dispersion and group velocity may be partially responsible for the experimentally observed drop of EDS, that is electrostatic discharge voltage, in devices based on thin film silicon on insulator SOI wafers. Thank you.